Hello, AP Physics C class. In today's video, we're going to take a look at the relationship between voltage and electric fields. And we're going to start this by looking at the equations. And we're going to sub in some electric field values in for the work done. So starting with our equation for voltage, our voltage is equal to work divided by charge, or work per unit charge. And in previous videos and previous lessons, we've identified the relationship between work done and electric field strength. And a reminder for that is work is equal to the negative of electric field strength times charge times distance, right? And work, charge times electric field strength is force times distance is work, just as a reminder how that works. The negative is in here because electric force is a conservative force. We'll talk about that when we get through energy. So let's combine these together. If you combine and substitute in QRE for work, you can get an equation that says that voltage is equal to negative electric field strength times the distance traveled. And rearranged, another way to look at this would be electric field strength is equal to negative voltage divided by distance moved in there. Let's look at this in a couple of examples. The first one we're really going to focus on is going to be on parallel plates. And in this equation, I showed, you can see a diagram of this in your notes for parallel plates. So let's look at this equation. And this one is represented in your notes. And it says that we have two parallel plates. The leftward plate has a voltage of plus 50 volts on it. The rightward one has a negative 50 volts on here. So what's the potential difference between these two plates? Well, it's just the difference between the two, 50 and negative 50. And that gives us 100 volts of potential difference. So that is the potential difference, or the difference in voltage between the two plates. The next part of the problem asks us to figure out the magnitude of the electric field in there. And here we're going to apply our equation. And we have the equation electric field strength is equal to the negative voltage divided by radius, or distance between. We have a potential difference of 100 volts. The separation of the plates is 0.02 meters apart. And we can find that the electric field strength here is going to be a negative 5,000 volts per meter. Realize that volts per meter is a equivalent unit to newtons per coulomb. This next example that I have up on the screen here is not in your notes. So if you want to pause it and try this one, in a moment I will show you the key for this. And there's the key. The electric field strength here for this problem is a negative 2,600 volts per meter. And it's the same idea for the previous problem that we just went through. Okay, so now that we've taken a look at just the equation that can be used to relate voltage and electric field strength, let me talk about this graphically. The slope of a voltage as a function of time or position graph is the negative of the electric field strength. And this makes sense with our E is equal to negative V over R expression. Here we have V as a function of R graphed. So the slope of V over R would be our electric field strength. But because it's negative, you can see here on our graph, at point B, we have this negative slope that's going to give us a positive electric field strength. If we're looking at trying to figure out the relationship for an electric field strength as a function of position graph, in this situation, it's the area under the curve that's going to give us our change in voltage, and that again will be negative. Looking at this in terms of not algebraically, but using calculus, you're going to see a couple of equations that are going to pop up in your reference tables. The first one is going to be the relationship between voltage and electric field. That is, voltage is equal to the antiderivative of electric field with respect to position. And of course, that's negative, and you see this in your reference table. The same thing, you'll see this equation actually twice in your reference table. They write it both as an antiderivative and as a differential equation. And in this expression, you have the electric field strength is equal to the negative dV dr. And this is the same mathematical relationship that we've talked about earlier with our equations relating voltage and electric field strength. These are just written as in the calculus perspective, as opposed to those written in the algebraic expression. Again, we have that little note at the bottom, just identifying the fact that because these forces are conservative, that we are going to have a negative involved here. So let's do an example of this. And in this example, you have a function of electric potential as a function of position. So V is equal to 4x squared minus 3x. And we want to know what's the electric field strength at position x is equal to 2 meters. Well, we have our voltage. We know that our electric field is the derivative of voltage with respect to position. So we're going to take the derivative of this, and that will negate it. The derivative of 4x squared minus 3x is going to give us 8x minus 3, but we have to negate it. So that will end up turning to negative 8x plus 3. To evaluate it at x equals 2, we would just plug in 2. So it would be negative 8 times 2, which would be negative 16 plus 3. Will give us a negative 13 would be volts per meter, would be our electric field strength at this position. This next example in your notes, I'm going to give you a shot if you want to pause it and try to solve this one. This one you're going to be using the antiderivative, and then I will show you the answer for this. And here you can see we're taking the antiderivative. We're evaluating this between 0 and 0.5, because we always need our bounds of integration for this. And you can see the substitution, and that is going to give us a voltage of 7 volts.